All right. Hello, class. Welcome again to one of our online lectures. This lecture is on orbital perturbations. Before I get started, make a couple announcements. So first of all, this is the week of February or March 24th, 2020. We are in the middle of online transitions to classes. I have not figured out exactly how the midterm will be working, but hopefully it will happen sometime next week. So that would be the week of March 31st. So hopefully on Tuesday we'll have a review session where we'll go over the practice midterm. And then on Thursday, with luck, we'll actually have the midterm. So be prepared for that. And it will not, of course, cover the material on rocketry or orbital perturbations, which we're covering today. It will cover everything through Lambert's problem. So we'll discuss that in the office hours later on. Okay, so what have we got here? So everything that we've discussed so far mostly has been variations on Kepler's equation, elliptic orbits, with some extensions, of course, to hyperbolic orbits and parabolic orbits. In this lecture, we are going to consider something a little bit beyond that. There's only so much you can do with elliptic and parabolic orbits. I gave you the roadmap of delta V's needed to get around the solar system. But it was limited to delta V's, limited to that restricted two-body problem that we discussed. And so in this lecture, we're going to consider what happens when there are other forces involved. So forces due to drag, forces due to the gradients in the gravitational field due to misshapen bodies such as the Earth, which has a little bit of a fat tire about it, or perturbations due to, say, solar wind, perturbations due to the moon exerting its own gravity field, failures, if you will, of the restricted two-body problem. And we'll show that they can be problematic in drag is problematic. You have to compensate for drag. But we also will show that they can be helpful in a way. So aerobraking, for example, is a way to get around that delta V budget issue. But also these gravity gradients can also be helpful. They can lift your orbit up, as in the case of lunar perturbations. They can rotate your orbital plane around. We're not going to go too far outside of the elliptic orbit paradigm. We're going to consider perturbations to an elliptic orbit. So we have a planet here. Let's see. Here's a planet, for example. We have an elliptic orbit going around that planet. And we'll show that we don't want to totally throw out the ellipse, right? Because it's a good starting place. And these perturbations are usually small. So we're not going to throw out the ellipse, but we'll consider variations on that elliptic motion, how the ellipse changes over time due to these orbital perturbations. So, for example, the Earth has a little bit of a fatness band here around the middle. And that can all cause the orbit to precess, so that your angular momentum vector will rotate over time. We're actually, today, in this lecture, this sort of big bite we're taking today, we're not going to talk about that particular perturbation. We'll mostly focus on the general perturbation equations and the effect of drag. So that's what we're going to focus on today. But then in the next lecture, we'll come back and we'll talk about this this effect of the non-circular Earth. All right. So let's move on to the next slide. All right. So what are we going to cover today? So as I said, we're gonna mostly stick to this quasi-elliptic motion, right? So here's, we'll make an Earth with some fuzziness around it, do the atmosphere, for example. We're in elliptic orbit, maybe, like that. And we're going to break down these perturbations into forces, right? The coordinate system that the forces are most naturally expressed in are these the satellite normal coordinate system, which we've introduced, but we introduced a lot of coordinate systems back in lecture 7. So we'll remind you what that is. And this is a coordinate system it's a satellite-centered coordinate system. And it's a coordinate system where the forces are fairly naturally expressed. And so we'll take those forces, right, we'll express them in the satellite normal coordinate system, and then we'll look at the motion. We'll look at the effect of those forces on these constants of motion, if you remember, right? Angular momentum vector, the energy of the orbit. We'll talk about how these forces change those, right? So we'll put a little dot above them. Oops. Put a dot here, right? So how those change with time, and then we're going to stick with these conserved quantities, the angular momentum and the energy. And we'll just talk about how they change with time in sort of this quasi-steady state manner. And then we'll talk about how those changes in angular momentum vector and angular momentum magnitude change the orbital elements. So a semi-major axis inclination, right ascension of ascending node, argument of periaps, and eccentricity. Today we're going to be mostly focusing on these two, the change in semi-major axis, which of course, if you remember, is a proxy for energy, so there's a direct correlation there, and eccentricity, so sort of a restricted planar motion of the system. So today, again, right, in that context, the most natural perturbation is atmospheric drag. Many planets have it. I think the only planet that really doesn't have it is Mercury, and we don't go there much anyway, so not particularly important. And we'll talk about how this. Mostly, we'll talk about it in the context of compensating for it, like as in we don't want these perturbations. So we'll talk about how the orbit decays over time if you don't compensate for drag. And of course, that has major implications for how much delta V you need to maintain if you don't want your spaceship or your space station or your little CubeSat to fall out of the sky relatively quickly. And then there's not as much we can say about this quantity, this eccentricity, but we will get into that as well, just to help us understand the problem a little bit better. Right. So, as I said, up till now, right, we've been talking about the restricted two-body problem, right, the two-body problem. The restricted two-body problem is what we think about when we're sort of moving between planetary bodies, or interplanetary exploration, going to the moon, going to Mars, that patched conic. We'll come back to interplanetary exploration later. Patched conic. We've been talking about the case where Kepler's laws are in effect, right? And when we're dealing with the patched conics two-body problem, there's not much flexibility we have, right? If you want to go from Earth to the moon, right? You've got to you're in a parking orbit. You give it some delta V, get out there. When you get there, you give it another delta V to inject into moon orbit, right? And then you put another delta V and you land on the moon. Another delta V, get off the moon. Another delta V to get back to Earth. And then finally, a negative delta V to re-enter. Although aerobraking probably is the most common way of re-entering the Earth's atmosphere. So again, delta V budgets are really the only way you can move it around in space if you don't account for these perturbations. However, of course, that limits what we can do, and there are subtle ways of getting around it using these perturbations, which can alleviate some of the burden on our delta V budget. Right? So we're going to talk about what those are. So up till now, we've talked about all the orbital elements are fixed, right? And now we'll talk about some effects which can cause them to vary with time. Again, we'll talk about it in the quasi-steady state. So we're always sort of in an elliptic orbit, but then we'll talk about how those orbital elements can sort of vary with time, assuming that the basic motion remains the same. So the ones you want to think about primarily in this lecture are drag, of course. We're going to focus on drag, right? Next lecture, we'll focus on the non-spherical Earth, because these are the two most commonly encountered orbital perturbations, drag and the non-spherical Earth, and they both have very large effects. So what we see here is an illustration of the non-spherical Earth. So the Earth is actually spherical. These don't actually show mountain ranges and stuff, although you can sort of see the mountain ranges showing up here. There's a mountain range. Those are mountain ranges. We're actually referring to, when we talk about non-spherical Earth, is the non-spherical gravity representation of the Earth, the non-spherical gravity field of the Earth. And what these illustrate, and these are caused by many things, some of which are non-uniform density of the Earth's core, right? So that some parts of the Earth exhibit are denser. They have more gravity than other parts, say here, which has low gravity, low density, if that's the cause. We will account for, although not specifically, lunar gravity, right? That's an important perturbation. There have been times where that's been used to boost satellites. So, for example, there's a very important work of Ocampo back in 2000, I think it was 5 or 4 or something. Ocampo. He became a professor at I think it was Hughes, and then he was a professor at UT Austin, where I did my undergrad, and then he went back into industry. But he was able to rescue a satellite which misfired. It was going for geostationary orbit, misfired. Didn't have enough delta V budget to inject that home entrance. Remember, going to geostationary it requires about 3.9 kilometers per second delta V, and he was able to use the gravitational attraction of the moon at high altitudes to lift the orbit up, to raise its perigee and get it up into geostationary orbit with the limited delta V budget that he had. Other orbital perturbations include solar radiation. So we do have a little example problem on solar radiation. Some of the interesting things you can do with that. The sun, right? Sun. There's the sun. There's the Earth, right? The sun produces a solar wind, particles radiating out from the sun, and those could, and actually just photons, right? Also cause solar radiation pressure. Mostly solar wind, and those can push spacecraft, especially spacecraft with large, I don't know what you call it, wings, if you will, large surfaces. On which the solar particles bounce off of. Right? And we won't actually discuss this one at all. Tidal effects. So remember the sea moves around the Earth. The Earth rotates, but the sea is tidal locked to the moon, and so it produces a little bit of extra gravity, which changes, of course, 2 times a day. Neap tide and what's the other tide? Two types of tide, the big tide and the little tide. So we won't actually discuss that in any depth, but there it is. A couple notes, right? Again, perturbations can be good or bad, right? They allow us to break free of the limitations of delta V budgets in some case. Think aerobraking. Within the restricted two-body problem, there isn't much you can do except with delta V, the gravity assist trajectory, slingshot maneuvers being an exception to that. And so if you can identify new forces, which you can represent or can control or can manipulate in a good way, that can reduce our dependency on that delta V budget. So that's the introduction. Now let's get down to brass tacks. And I should confess, I should say, that I guess many students don't find this the juiciest part of the course. I guess I can put it that way. Maybe seems a little dry, especially this first part of the material where we have an arbitrary force, right? Some arbitrary force. We don't know where this force is coming from. Could be drag. Arbitrary. Could be drag, could be gravity gradients, could be lunar perturbation, could be anything. And we're going to look at how those forces affect the angular momentum vector and the energy. And then we'll look at how those generic forces change the orbital elements A, I, E, omega, and little omega. Not looking at true anomaly, however, of course. So, okay, with that warning, all right. Hopefully, you have your coffee, and you're ready for to go through these. And if you go to Prussing, I think chapter. Let's see which chapter is Prussing. Chapter 11. We're covering. Chapter 11, it's about page 200 or so. He goes into, or Prussing and Conway, they go into more detail on these orbital perturbations. We're going to skip through some of the derivations, especially the derivations of these orbital elements, the orbital plane ones, because they involve vectors and they're very complicated. So we'll just sort of, we're not going to ignore them. I don't cover them, but we'll do them more quickly, really focusing on the A and the E because they're just a little bit easier to deal with. So first of all, we've got a generic force. Right, this is your satellite here. There's our spacecraft. It's got its little solar arrays there, right? And the force, right? So a natural coordinate system for representing forces from the satellite's perspective is the satellite normal coordinate system, because most of the major forces we deal with are best represented in this coordinate system. So it's easy to figure out what the n component, the r component, and the t. So this is also occasionally called the RTN coordinate system. I think it's also the Fernet coordinate system, although don't quote me on that. Of course, you may actually end up quoting me on that. But okay, so what are these R and T? Well, the letters are somewhat evocative, so they're hopefully easy to remember. There's a N for normal. So normal meaning orthogonal, not normal as in like that's my normal thing I do. So normal, so the E hat N unit vector, this is a unit vector of course, is the one that points out of the orbital plane. So this is the orbital plane. So you can't really, it doesn't really look like it from this like diagram here, but this N here is out of the plane of the orbit, right? So it's perpendicular to the orbital plane. So the normal, think of normal, perpendicular to what? Perpendicular to orbital plane. So for example, drag, well, unless you have some lift, doesn't typically have a normal component. However, the perturbations to the Earth's gravitational field does. So that's the first coordinate. The second is radial. R stands for radial. Radial. And so, as you would indicate, this is in the radial directions, the one pointing from the center of the coordinate system, which is typically the center of the Earth, to the spacecraft, and then out beyond. So in the radial direction, right? So in the direction of the radius vector. So r hat direction. So r is for radial. And then T is a bit of a misnomer, but it's easy to remember anyway. T for tangential. Tangential. Right. So T is actually just the direction which is orthogonal both to the normal and the radial vector. So it's actually not tangential to the velocity, right, which would be sort of what you'd think of as tangential, but it's sort of, if you were in a circular orbit, it would be tangential to the velocity. It's just the one that's in the plane, perpendicular to the radial vector. So in plane, perpendicular to the radial coordinate. Right. So again, radial points from the Earth to the in the direction of the r vector, r hat vector. N points in the direction of the angular momentum vector. Again, we're assuming quasi-steady state, so we're assuming that's well defined. And T is just what you get by crossing the other two unit vectors. Right. Note that the tangential direction is not necessarily in the direction of the velocity, although it can be, right? This could also be negative, by the way. So, if you're going the opposite direction, if you have a retrograde orbit or something like that. Right, so tangential, radial, normal. Right, so now we have so we've decomposed our force into the three components from the satellite's perspective. So for example, due to drag, this is the tangential is most dominant. The normal, you often get that from the perturbations to the gravity field of the Earth. And radial, well, you can think of maybe if you're orbiting the Earth, right? There's a moon out here. That's sort of in the radial direction, so that would be maybe a large component in the radial direction. Moon, E hat R. But of course, over here it would be the opposite direction, and E hat, and here it would be in the E hat T direction. It's negative. Okay, so the question is then, right, in the quasi-steady state analysis, how do these forces change our orbital elements? Right? Those are orbital elements. Again, ideally in sort of in a true coordinate system, we would just integrate motion, right? We would have the gravity rederive all of Kepler's equations or whatever. But that's a lot of work, and it's really hard to get a grasp on. So we're just going to consider that these forces are relatively small or periodic. They don't repeat. They don't have large effects on these orbital elements, and so we'll sort of take this quasi-steady state approximation. Right. So, right, as we talked about earlier, right, very first lecture kind of stuff. The orbital elements are intrinsically tied to our conserved physical quantities, the angular momentum and the energy. So specifically, remember, energy is linked to semi-major axis. The magnitude of angular momentum combined with energy gives us the eccentricity, and then the direction of the angular momentum vector, this part, right, is what gives us the orientation of the orbital plane. Right. So initially, we're gonna focus on A and E. We'll also talk briefly about the other ones. Just remember, we can express these orbital elements in terms of these physical quantities. So this is the z component of the angular momentum vector divided by its magnitude. There's the x component divided by the y component. So these depend on the direction of the angular momentum vector. And these other ones depend on the magnitude. So these ones are a little bit easier to calculate. That's why we focus on them, because calculating the magnitude of these changes is a little bit easier than calculating the changes in direction. Yeah. Let's see, notes here. Again, quasi-steady state. Momentum and energy are not truly conserved in the perturbed model. But we assume that that these rates of change are relatively small, so at any moment in time we can sort of pretend we're in elliptic motion and just calculate the rate at which our ellipse is changing its shape over time. Okay, so how to do this, right? Well, let's look into it. So again, first of all, we're going to find expressions for the rate of change of our physical constants of motion, specifically angular momentum vector and energy, and then we'll translate those into using the chain rule primarily changes in our orbital elements. So remember from the previous slide, we have a formula. We can express the formula for semi-major axis and eccentricity in terms of these physical quantities, the scalar versions, right? Scalars. Right? And that simplifies our use of the chain rule, right? Because they're scalar quantities. Right. And so it's actually relatively easy. A is mu over 2e, right? So it's relatively easy to then calculate A dot, right? Just using the chain rule, right? That's dA dE, right? Times dE dt. So this thing here is E dot, right? In this, we just have to differentiate this expression here with respect to E. It's just 1 over E, so it's relatively easy. We get 1 over E squared. The negative sign drops off because it's a negative exponent. And so we get a relatively simple expression, tame expression for A dot right here. So this assumes, of course, we can find E dot, right? E, of course, we know, right? Quasi-steady state approximation. We just get that back from A. But E dot, of course, we'll have to figure out what that is in a minute. Next, eccentricity. Now this is a little bit harder, of course, because it depends on both E and H, right? That's the problem. So again, using the chain rule, right, representing this as 1 plus 2e h squared over mu squared to the 1/2, right? We can differentiate with e with respect to h, and then multiply by h dot. Plus, this is where the chain rule comes in. Differentiate e with respect to energy, and then multiply that by e dot, right? So if we can find expressions for h dot, the scalar version, and e dot, then and of course we can now differentiate this expression with respect to h and with respect to e, it's sort of almost the same. Then we can find an expression for the rate of change of the eccentricity. Right. So how do we do that, right? Well, I mean, differentiating this bit here with respect to e and h is not that challenging. It's just again, pull that down, the exponent down, right? Then we have a 1 over 1/2, and if you simplify the expression out, and you can go into processing if you want more details on this, you get more or less the same expression for both e and h, right? Because they both show up here. H, however, having a 2 in front of it, and there's another term of h which pops outside and cancels something else. So it's a relatively simple expression for E dot as well in terms of big E dot, which is energy, and H dot, which is angular momentum. Right. So now clearly the goal, the important thing to do is to find expressions for these two quantities, because we know A dot, right, and E dot in terms of H dot and E dot. And so the goal now is then, of course, to find expressions for H dot and E dot. So how do we find that? Well, here we have to think about the physical quantities. What is H? We have to go back to those forces, and how do forces produce changes in energy, and how do forces produce changes in angular momentum. Right, so this is sort of Newton's law kind of stuff, right? Just basic mechanics. So energy, we can look at energy first because it's a little bit easier. Energy, remember, work is force times distance. Right. Force times distance. And so, well, what's force times distance? Well, now we have a bit of a problem because we have a vector valued force, right? So, okay, so there's a vector value of force, and then the distance, right, is our change in our position vector. And emphasize vector there. Well, everything here is pretty vector oriented, so is there any way to simplify this expression? Well, okay, so first of all, let's divide the whole thing by dt, right? And we get E dot on the left, and that dr over dt becomes velocity, so that makes life a little bit different, so simpler. And then if you remember back to, I don't know, lecture 5 or something like that, where we drew this triangle. Here's the satellite. This is R, right? And this is the radial direction. There's the tangential direction, and the velocity in the tangential direction was r theta dot. So the distance, this r, times the rate of change of theta here. So that's that's also f, right? And so we have the tangential component is r theta dot, and we have the radial component is of course the rate of change of this magnitude, which is just r dot. So we put those in the satellite normal coordinate system. RTN coordinate system. And of course, this is already in the RTN coordinate system. And so we could just take the dot product of those two vectors. This is r dot r theta dot 0, right? Just take the dot product of those two, and we get an expression for E dot, a scalar expression for E dot. So that's nice in terms of r and t, and r dot and theta dot. Right. So that's nice. We don't, of course. So we'll need to simplify these expressions, of course, later on. But for now, that's what we have. Likewise, we look at the angular momentum. Well, what is angular momentum? Rate of change of angular momentum. That's torque, right? So force crossed position vector. Torque, right? Assuming the sort of normalized angular momentum component here. R, right? Well, what is R in the RTN? We have force in RTN coordinate systems, and so now we just write down radius in RTN. Well, that's easy. That's just R 0, 0 in RTN. Can't make ends. So we cross those two vectors together. You do standard cross product formula, and you get this expression here. Notice that there's, of course, no component of the angular momentum change in the radial direction. So that's interesting. Okay. So there's a component in the tangential direction and a component in the normal direction for H dot. Now this is the vector value, mind you, not the scalar value. And so we actually we want to take the we also want to take the rate of change of the scalar value. And so what is the scalar value? Well, that's like the vector value, right? Transposed with itself divided by the magnitude. Right, and so we use the chain rule on that. We get two versions, right? There's this H vector dot pops in there, and now we've got we've just found that term, so we can plug that in here, and then of course the magnitude of the angular momentum, right, is just the magnitude, and it's all in normal direction. So this is 0, 0, H, right, in RTN. We take the dot product of those two values, and then everything cancels out. Right? This is orthogonal to that, so that disappears, and then we just have the product of those two. There's an H squared, so that disappears. We just in the end we just get RT. So the rate of change of the angular momentum vector is the distance times the force in the tangential direction. Right, so a very simple expression. Of course, all of this implies that neither energy nor angular momentum, neither the direction or the magnitude, is conserved. Disturbances can create or add energy to your spacecraft. So, for example, drag decreases energy, but solar wind, for example, can increase energy if it accelerates the velocity. This all comes from again we talked about a quasi-steady state approximation. So all these things are valid, and this is just RTN in the RTN coordinate system from lecture 2. And so yes, we went through all of this. Okay, so now we've got an expression for E dot, and we've got an expression for H dot, although we won't use it in this slide. So now we are possibly ready to find an expression for A dot. So remember, A dot is this term here. Well, this is easy to. This is mu over 2a, negative mu. Well, the magnitude is just mu over 2a. This, however, is slightly more complicated, right? It's given right here, And really we want to express all of these in terms of the current orbital elements, as well, of course, as in T and R. Right? We want to, in particular, get rid of R dot and theta dot. Right? Well, theta dot, what is theta dot? Well, theta is a combination of omega plus F, right? The only one that's changing, however, is F. Well, actually, omega dot is changing slightly, possibly due to perturbations, but we're going to assume that's 0. And we're assuming we're in quasi-elliptic motion, so then theta dot is just F dot. F dot, as we remember from way back when, is we had that expression. This is Kepler's third law, right? H over R squared. So in R, of course, we can use that expression over there. So that gives us an expression for theta dot, right? The expression for R dot is a little more complicated. So I've got a little note here on the notes. So if you remember, R is this term here. If we differentiate this, use the chain rule, we get with respect to F, we get this expression times F dot. We then use our expression from F dot here, right? F dot equals H over R squared. And so we plug all of those terms in, and it simplifies out to simply R dot is mu E sine F over H. Okay. So we go back to the previous slide, and then we plug that term in for, so I want to indicate that's the note, right? And this term comes from there. So we now have expressions for both of these terms in terms of orbital elements, also H, but H is a constant of motion, so that's okay. And so we plug those in, and we get this expression for A dot. So here's the R term, and here's the theta dot term. Okay. So obviously the theta dot term is a little simpler than the R term. The T term is a little bit simpler than the R term, but there we go. So we can simplify this a little bit more to get rid of the H's, right? To get rid of the R's, plugging into the polar equation there, to get a relatively simple expression here, expressed only using orbital elements. Right. So this is the expression that we'll be using primarily for the rate of change of the semi-major axis in this lecture and in the next one, expressed in terms of the forces. Again, these are arbitrary. They could represent drag, they could represent gravity gradients, they could represent solar wind. So A dot was as simple as it gets. Now it sort of goes downhill a little bit. Not too fast downhill. So the next step is to find E dot. Right. So from our previous, about 3 slides ago, we had an expression for E dot, right, in terms of H dot and E dot, energy, or rate of change of energy. So this one, remember we dealt with that on the previous slide. We also had an expression for H dot, which is actually in many ways simpler than the expression for E dot. It of course requires us to plug in R there, right, from the polar equation. And so if we combine these two terms, right, we got here H dot, it has a T component, E dot has a T and an R component. We plug all those terms in, and we group them by T. So remember, T has 2 components, one for this term energy change, one for angular momentum change. and R just has one component for energy change. And so that's relatively simple. It's the same expression we had on the previous slide. So there's obviously some manipulations going on here. We have something new popping up here. That's where we use the other version of the polar equation, right? So this is the other version of the polar equation. Alternative polar equation. Why did we use that? Well, because basically, these expressions are getting quite messy. And so it turns out, right, that if you use that version of the polar equation, you can get this common term on the outside, and it just simplifies everything. So all of these things don't have different coefficients. They all sort of have the same coefficient. So again, I emphasize, however, I wrote ECC here to emphasize that this is the eccentric anomaly and not energy. I know I'm using the same symbol. Right, and it's a bit confusing that way. Prussing and Conway use like a little script for energy. But I find that tiresome, and since I'm not going through these derivations in great amount of detail, I don't. Right? So I use E far more than I use eccentric anomaly. So in this lecture, so that's why. Okay. So and then of course, right, the relationship between F and E is right. We know what the relationship is. That's from that other lecture on geometry. This is not, it's not the best equation because, right, you do have this mismatch between terms, but I don't know what you're going to do. We don't do much with E dot anyway in terms of without considerable simplification. So there you go. Right, now we're getting to the really the harder bits of this generalized analysis, right? So now we're getting to the terms which define the orbital plane, right? So I'll draw an orbital plane here. Here's our planet, right? Here's our orbital plane. Remember that here's the equator, equatorial plane, right? Remember, inclination is that one. The angle from right ascension is the right ascending node, and then the angle to periaps is the argument of perigee. So again, these are orientations of the ellipse in three-dimensional space. And as such, remember, we're going to have to remember those three rotation matrices from perifocal to Earth-centered inertial coordinate systems. That rotation matrix, I think it was R3, I want to say omega, R1, I. So there's three rotations and then R3, which is theta, which is sort of omega plus F. So from PQW to ECI coordinate systems, right? Yeah, so we're pretty much doing the same thing, RTN to ECI. And so we'll need to like transfer our forces to the ECI coordinate system in order to get the changes in these orbital elements. And so that's a bit of a mess. And so, yeah, that's a bit of a challenge. But we can get through the, it's all in Prussing, Conway in glorious detail. We're going to just cover the basics, give an idea of what's going on. So inclination, right? Maybe that's the simplest. The hardest is argument of perigee. because it combines several things. The first is inclination. Remember, the formula for inclination was that z component in the ECI frame of the angular momentum vector divided by the magnitude, right? And that in the ECI component frame is important because we're going to have to translate these forces into the ECI coordinate system, and that's what makes this bit of a mess, right? Okay, so all right, well, that's given that we can differentiate the whole thing with time, right? Divide by, well, when we differentiate it with time, right, we get a sine term here. We divide by the sine term, right? That's sine I dot, right? Divide by that I on the right hand side. So that's where that sine I comes from. And then we apply the chain rule to this thing, right? So first, of course, we get h dot z. That's the easy part, right? Those two cancel. And then we get the other part, right? It's 1 over h, negative exponent. That's where the negative sign comes from. And then we apply we get an h squared on the bottom, and hz doesn't change, but then we get an h dot here, right? So, which just standard application of chain rule. The trick, of course, is to figure out which hz is. The other part, h dot, we're in good shape with, but h dot z is the mess. So I think I've got like, so how do you find these components of h dot? Well, actually, finding the components of h dot in the RTN coordinate system is easy, right? It's just, right, we already have an expression for it, right? So this we already have, recall. And then we can put it in in vector form. But then what we need it in is ECI, right? So we need these things in ECI. And so for that, we have to get this rotation matrix, which is a combination of these 3 rotation matrices. And at this point, I decided it's just not worth putting on the slide. So C, Pressing, and Conway, Chapter 11. And they go through it in glorious detail. It's like page 200 or something like that. Okay. So again, right, this expression, that's the tricky bit. But once you have the expression, right, first of all, it's nice that it only depends on the normal component, which is what you would expect, right? Just change color. So this is the normal to orbital plane. Remember, the only thing we're changing here is the orbital plane, the orientation of the orbital plane. Right. So the only component of the force that should matter is the part of the force normal to the orbital plane, right? So that's the n component. Right. And that's true for both right ascension and inclination, right? The only component that matters is the part normal to the orbital plane. Right? So again, you plug it in. I'm not going to go through the details. Again, for right ascension, similar right ascension of ascending node. Remember, that's the angle that this plane makes with the first point of Aries. Remember, we had a formula for it. But again, this formula is in ECI coordinates. So these are the components of angular momentum in ECI coordinates. We can apply the chain rule to this, right? You differentiate tangent, you get cosecant, right? And then the chain rule, theta dot. Move this cosine square to the cosecant to the right-hand side. This is the chain rule applied to this, right? So again, just the same as we had over here, except now the denominator is hy as opposed to h. And so we now have a component of h dot y and a component of h dot x. Right. So 2 components, right, that we have to worry about. Neither of which did I actually write down the expression for on the next slide, just because you can take that term and multiply it by the rotation matrix, but it gets quite complicated. Actually, I don't even think they have the full expression for either of those terms in Pressing and Conway. They just like skip that step. Right? They do pretty much what I'm doing. But in any case, what you get is something that's mostly well, you got the magnitude, right, which is all good, but you need the so there's the physical stuff here, and then the rotation matrices. This is theta, right, and so we express we have an expression basically for omega dot. So this is the precession, if you will, of the orbital plane. This is the dipping of the orbital plane, I dot. It moves up, rotates back down, right? The precession is, so that's omega dot. Yeah, sorry. Should be, someday I'll get better at drawing this stuff, or maybe my handwriting will get it better, or maybe not. Any case, so the orbital plane dips, right? According to this term, it precesses, it rotates about the North Pole due to that term. And finally, there's a very complicated expression for, these terms both depend on the component of force normal to the orbital plane. And then finally, we have an expression for the argument of perigee, where in the orbital plane perigee is located. And this is the most complicated expression we have. So, right, if you think about here's your orbital plane, here's periaps, here's your planet, here's periaps. This is where argument of periaps is. What's going to force that periaps to move over here, right? Prime. What forces that periaps? Well, I guess if you push in the tangential direction, right, that should force the periaps to move forward a little bit, the ellipse to rotate. If you push out in the radial direction, well, what's that going to do? Well, that's going to sort of expand the bubble here, and so it should move the argument of periaps in the opposite direction. So I'm like running out of sketch paper here. All right, so a tangential force, I would think, would sort of move that argument of periaps forward. This is the T component. And then I would think that a normal or radial component should move that periaps backwards, right? So negative delta omega, positive delta omega. And this is for the radial case. So radial case and tangential case. So we'll see if that's true. So if we look at this expression here, we see the tangential component here. It in fact actually quite right here. It has a positive coefficient, so the tangential forces tend to move the argument of periaps forward in the orbital plane, and radial components tend to move it backwards, right, in the orbital plane. So that's what we're seeing from this expression. There's also this non-trivial term with the precession of the argument of periaps coupled with the inclination, which is actually just a geometric thing. This is not a new perturbation. You notice there's no forces here. This is just a result of geometry, right? So you've got your orbital plane here, right? If the inclination change, so for given inclination, if this argument of periaps changes, then that automatically causes some change in the for fixed all the other orbital elements fixed causes some change in the argument of periaps. Right, so that's So this is these two are directly caused by the forces. This is also caused by the force, but it's coupled through this equation, right? So changes in omega dot lead then to changes in the argument of periapse. So again, very complicated formula. The derivations don't go through in much detail at all, but you can sort of get the intuition as to what's going on. Radial forces move the argument of periapse forward. Tangential forces move it backwards. Tangential force moves forward. Radial components move it backward. Our changes in the right ascension move it backwards. And then normal components will change I and omega. Right, so that's all. That's the dry part. Well, I don't know. The rest is kind of dry too, but it's also now we've sort of covered the dry bit, and we get a little bit juicier. So we can take a break if you like, and apply these now to something a little bit more interesting. So this is actually a very interesting question. You can do really interesting things with these orbital perturbations. And the first interesting thing that we're going to do is levitate an orbit, which is sort of magical, isn't it? Right. So this is not actually a levitated orbit. This is a illustration of a surveying satellite, not a levitated orbit, but it's a polar orbit, which is why I used it. Scanner, mapping satellite. All right, but we're going to use it as our illustration anyway. So because the forces work out a little bit better in this case. Now this is not actually a levitated orbit. This is a simplified levitated orbit. Right. So you'll see the reason for it in a second, right? So we've got a satellite, mass 100 kilograms. Now the mass becomes important because you need to normalize these forces per unit mass. So mass becomes important. It's in a circular polar orbit, right? Circular polar orbit. High orbit, 42,000 kilometers. That's radius, of course. And we assume it's there's a sun over here. Let's see if I can draw the sun somewhere. Right, here's the sun. Right. And the sun is causing solar wind, right? And you can see what's wrong here is that actually, right, the solar wind is not perpendicular to a polar orbit, right? So, but it simplifies the geometry a little bit, right? So in reality, you would want this orbit to be perpendicular to the sun and not a polar orbit. So, you know, in reality, it depends on the time of year, right? This would be the North Pole, right? Something like that. So this would be winter. Right. But in any case, okay, let's assume that, right, we're in an Earth with no seasons. So we're in a polar orbit. Our orbital plane is perpendicular. This is the E hat n direction. Our orbit is perpendicular to the sun, to the direction of the sun, and so we have this force due to solar wind due to the sun. And so it creates a force of 0.1 newtons in the E hat n direction. Well, actually, I guess the E hat n direction should be pointing the other direction. Right. So 0.01 in the E hat n. There's no component r equals 0 in the radial direction, obviously, and no component in the tangential direction. Right. So in reality, of course, this orbit is true. It's just, right, the orbital elements are slightly different because it's measured in the equatorial ECI coordinates and not the heliocentric coordinates. Right. In any case, so our first step is to calculate the RT and N. there's actually only one of these components, T equals R equals 0. So we take the force, we normalize it by mass, right? So we get a normalized force of 1 times 10 to the negative 6, right? 10 to the negative 6 kilometers per second squared. Right, normalized force. Eccentricity is 0. Our true anomaly is the same as our centric anomaly, is the same as our mean anomaly. It's just NT, right? So we can simplify that expression. And so now we can look at the various perturbations to the various orbit elements, right? So first of all, we'll look at semi-major axis, energy of orbit. Now, we can already tell that there's not going to be any change in the semi-major axis because all the forces are perpendicular to the orbital plane. And this plays out because R and T are both 0, right? And so the whole expression is 0. Our force is only perpendicular to the orbital plane. Likewise, with eccentricity, again, right? There's no perturbation to the ellipse, right? There's only a perturbation to the orbital plane. The R and the T are both 0, right? And so the semi-major axis, the eccentricity doesn't change, and the semi-major axis don't change. So no changes there. Now the other orbital elements, there's no argument of periapse, obviously. Omega dot, we should just mention that because, right, there's no eccentricity because omega is undefined. So we're going to ignore that. Next, we look at inclination, right? So now we do expect significant changes to inclination. And so we have our armed with our formula for inclination changes. We have this big nasty expression here. Fortunately, in our case, most of these things we can get rid of. There's no argumented periapse. This is just NT. This is 0. This is 0. So we get rid of that expression. And so the only thing we have left is mu over A, or A over mu. Sorry, screw over A over mu. And then, of course, cosine NT. Right? So we have a relatively simple expression for the change or rate of change of the inclination. And you can see it's periodic, right? It cycles between 0 and 1 back to 0 and negative 1 and 0 over an orbit, right? This is over the period of an orbit. We can integrate that out to find the net change in inclination. So this is typically what we do, right, when we're looking at these secular perturbations, right? So I'll just mention the secular perturbations. We'll talk more about secular perturbation in a second. That's because we integrated. Right. So net change in inclination over time. And so if we just integrate cosine, we get sine, right? And so the overall net change in inclination, so the original inclination was 90 degrees, and this is our change. So our actual inclination is, over time, 90 degrees plus this term right here. Likewise, we look at now the expression for right ascension of the ascending node, right? So here's our orbit. This is a levitated orbit, right? It's a better version because it's what you want. We'll talk about this example in a second. Right? So what was I saying? Oh yeah, so the right ascension, right? So in our case, of course, we're a polar orbit, so our changes in right ascension are a rotation in that direction, delta omega, right? Pushing it a little bit back on this side, and then sort of forward on the other side. So we have this big nasty expression, of course, for right ascension. It depends on the normal force again, which we've already calculated. Most of these terms disappear, right? That goes to 0. This is not important. This is nt. This goes to 0. Sine of 90 degrees is equal to 1. And so the only terms we have left in against are a omega, or a mu, and then sine of nt. Right? So similarly, right, well, we don't know what our original right ascension was, and so we don't actually know what our absolute semi-major is. So assume this is 0, right? So omega naught equals 0, and so we could just say that our right ascension is, again, periodic, right? We integrate this term, by the way, of course, to get the secular perturbation. And we get that the absolute right ascension of ascending node is this term right here. Right. So, so what is the magnitude of this change, right? So this is a change of orbital plane out at a radius of 42,000 kilometers. So if you multiply 0.054 radians, so at a radius of 42,000, we get actually a motion or a displacement from the original orbit of 188 kilometers, right? So if we think about what we're displacing here, right? Here's our planet, right? Here's our orbit. Here's our nominal orbit. Here's the actually. Just erase that. So here's the equatorial plane. So if we look at the displacements from a nominal orbit, well, there's 4 points that we can look at. Let's see. Make some colors. Actually, I'm going to do that one and let's see, make it orange. So at the ascending node, so this is the ascending node. At the ascending node, if we plug in, well, nt is or theta is 0, right? We get that we're being so that the displacement, right, delta omega, right? The inclination doesn't change our position, right? Delta I doesn't change our position, but this this change in right ascension does, because it pushes our ascending node back by an amount of 188 kilometers. So it pushes the ascending node back, right? Because the right ascension of the ascending node is increased. At the descending node, at the other side of the orbit, right, the right ascension is pulled back, but pulling back at that point of the orbit actually pushes in the same direction as pushing forward on the other side of the orbit. So that's also 188 kilometers. Now at the North Pole, right, we don't have to worry about, so we're up here, we don't have to worry about changes in the right ascension, but we do have to worry about changes in the inclination. So at the North Pole, we get a positive change in, it says E hat N. So we get a positive change in inclination. So if we go back to these expressions, so here we've integrated at nt equals 90 degrees, right? This term is positive. And at nt equals 270 degrees, that term is negative. Right? So now if we go back to our orbit here, so we're pushing. So we've at the North Pole, we've increased our inclination. So we actually pushed it a little bit that way. And at the South Pole, our inclination is decreased. So we've been pushed that way slightly. So I think I've got my numbers backwards here. So at the ascending node, so at the ascending node, this is equal to 0, and so the change is negative, right? Okay, so at the ascending node, we have actually a negative change, and at the descending node, we have a positive change. So I've actually got this all backwards, so I apologize. I'm not going to re-record the lecture, but so hopefully you'll bear with me. So actually, we've moved that way by 188 kilometers, and here we've moved that way by 188 kilometers. So I apologize for the mistake. Right. So at all points in this orbit, the orbit is sort of tilting around. I don't know, like a coin that you've tossed on a table. It sort of like spins around, and so the orbit, the point in the orbit, is always about 188 kilometers above the actual orbit. So that's called a levitated orbit. The application here is that it is actually proposed in this recent paper by Begg and McInnes. Actually, I'm not sure. McInnes. And the idea is that this geostationary, satellite track is very crowded, and so the idea is to levitate another stack of geostationary satellites 188 kilometers above the existing geostationary stack to make room for more satellites. Because these things are expensive. Well, they're not expensive because they give away the free, but they're limited in the number of slots you can get. So make room for more GTO satellites. All right, so that was an interesting example. Now we're going to get to, and now things will go a little bit faster, probably. So now we're going to get to a very particular form of orbital perturbation, namely the perturbation due to drag. Have a little bit of coffee. If you want to take a break, have a coffee. Now's a good time. Have some. So, what we saw in the last slide was what's called a short period perturbation. So if we look at the orbital elements over time, say in particular I and omega for that one, and we integrated those, so we looked at the actual orbital elements over time. Over time, what we saw is that they look sinusoidal. Right? And that's called a short period perturbation. So it's a perturbation which comes and goes over every orbital period, but doesn't accumulate and doesn't change from orbit to orbit, right? Fixed from orbit to orbit. So if we look at this, right, this is the well, actually, this is an orbital period here. So the short period oscillations are ones that, well, typically we think of them as intra-period. So ones like, so sinusoid was the one we had. Actually, let me erase that. Get a better looking sinusoid here. Right there. There's a nice short period oscillation, one that disappears at the end of each period. It can reappear at the end of the next period, but for each orbit, right, it comes and goes, right? So that's a short period. Or it could be even shorter than, so actually the period is like, yeah. Actually, let's see, that's the period, I guess. So a perturbation that comes and goes over less than one orbital period. By contrast, we get long period perturbations, which last longer than a single period, so they don't just come and go over it, but they don't accumulate. Longer than one orbital period, but neither of these accumulate. They don't increase in magnitude, and well, I guess they can increase and decrease in magnitude, but they don't do so secularly, and they don't drift. Right. So the mean stays the same. Yeah. So short period and long period perturbations are one where the mean stays the same, but in the short period it moves faster than the orbital period. So this is again right levitated orbit kind of thing. And the long period ones, which are ones which act over multiple orbits, but again disappear over time, don't have any change in the mean. These are mostly harmless. Or even beneficial. In contrast to what obviously is the other case, which is the secular perturbations, and these are ones which accumulate over time, so that you don't get back to where you started. Right? And secular perturbations, well, they can be beneficial if you don't. They happen. So, for example, inclination, right ascension will tend to drift over time, and they'll drift substantially. And if you don't want that to happen, if you want a stable elliptic orbit, you have to compensate for them. But really, honestly, there's very little you can do short of a frozen orbit to compensate for secular perturbations. The exception being in the case of drag. Where you've got to keep boosting your satellite or your spacecraft in order to not fall into the atmosphere. So the biggest source of secular perturbations is drag. I don't. The gravity perturbations are also a significant source of secular perturbations. But we're focusing on drag. So where does drag come from? Well, drag comes from the fact that space is not empty. Right. Space is full of particles floating all around. Some of them come from solar wind. There's little helium particles floating around all over space. But you don't usually have to worry about those. What you really have to worry about is particles that fly out of the atmosphere. So here's our Earth. I'm getting tired of the red, so I'm going to switch back to orange. Here's the Earth, and floating around the Earth, right, into space are particles of atmosphere. So obviously we breathe. I'm talking, so obviously we have an atmosphere here. There are lots of particles here down on the surface. But those particles are a gas, and they are held in place by gravity to some extent. But, right, gases will expand if they're not, if there's no rigid barrier. So the more pressure you have, obviously, the more the gas is forced down. But it's not a perfect process, right? So there's PV equals nRT. The density will decrease, right, as you get farther away. But it's a continuum, and all into space there's particles of atmosphere. And that wouldn't be the worst of it, except that the particles of atmosphere in our atmosphere, especially at the top levels of atmosphere here up in the ionosphere, interact with the magnetic field, and they interact with solar wind in interesting ways, so that they don't fall down to Earth, or they're constantly excited, and their densities change over time, right? So we'll come back to that in a bit. Let's just go over the basics, right? So first of all, right, we've got, let's go over the basics. We're here on Earth, right? Here, us. Airplanes, right, use atmosphere to fly. They generate, we have airplanes here, right? That's my airplane, right? They have lift, coefficient of lift, and they have coefficient of drag, right? So airplanes, the aerospace people, aeronautics, they like atmosphere, right? Because they can't fly if they don't have atmosphere. We don't like atmosphere because it gets in our way. Because we don't usually deal with CL, we only deal with CD. So up until 14 kilometers, 20 kilometers here it says, we have airplanes. Airplanes can fly up to about 20 kilometers, at which point they're not fast enough to generate enough lift to overcome drag, or to overcome their weight. Right. So airplanes are limited to here. We have balloons, which can go higher than that. So that up to about 50 kilometers, right? The balloon will you can get a balloon big enough to overcome its weight. Above 50 kilometers, that's when things start burning up, right? So specifically, we have this Kármán line, right? The Kármán line, and the Kármán line, right? So anything below the Kármán line will burn up, right? Right. So the Kármán line has several interpretations, actually. Did something happen on another slide? Don't think I... Okay. So the Kármán line has several interpretations. We'll talk about them later. So the first is that below the Kármán... So the Kármán line is 100 kilometers altitude. Right. And below the Kármán line, we get the aero people, the aero, right? And above the Kármán line, we have the astronautics. We have astro people. So if you're astro specialization, you work up here, and the aero people, they work down here. Right. So what's the interpretation of the Kármán line? Because the Kármán line was proposed by Theodore van Kármán. He died in 1963, not that long ago. But basically, the Kármán line is the density of atmosphere, and it's sort of like a mean density, because actually below the Kármán line, that density is pretty reliable. But it's the altitude at which a generic airplane, above which a generic airplane would have to be going faster than its orbital velocity in order to generate more lift than it has weight. Right. So remember, the orbital velocity near the surface of the Earth is like like 7 kilometers per second. Right. So above the Kármán line, an airplane would have to be going 7 kilometers per second in order to generate more weight, more lift than it has weight. So that's the interpretation. So this is sort of the dividing line between orbital problems and aerospace problems. Although, honestly, right, I mean, airplanes don't fly above 20 kilometers because, right, they can't go 7 kilometers a second, right? That's unrealistic. The other interpretation, of course, is that an orbit, any spacecraft below the Kármán line will not survive a single orbit. Right? That's the other interpretation. Right. So anyway, you got things burn up below the Kármán line. You have the Kármán line, and things above the Kármán line. We have here. It's called the thermosphere. I am broken down here, I guess, into mesosphere and ionosphere. And then, so we call them different things. I think the ionosphere is important because that's where things start acting up. There are models of the ionosphere change with time. So the ionosphere, mesosphere is pretty well behaved, but the ionosphere starts causing lots of problems. And here's our Kármán line, actually. Actually, that's 90 kilometers. Right. So here's where things get dodgy, and this is also our astrospace. Right. So the ionosphere keeps going, right? It goes well past 350 kilometers and can go much higher, depending on solar activity. We'll talk about that. And of course, it's called the ionosphere because that's the area of the atmosphere at which all the particles get ionized. So you get radiation ionizes these particles. All right. And yeah, here we see an image of the aurora borealis. The aurora borealis, right, is caused by ionized particles interacting with the magnetic field of the Earth and the Sun, and you can see it's expends well on space, right? So that you have things flying close to the aurora borealis. Right, and so obviously there would be no aurora borealis if there was nothing up there, right? So aurora borealis, just an illustration that there is atmosphere and a significant amount of it up in space, although it behaves differently than it behaves down on the Earth and is much less predictable. Right. So how bad is it? What about the situation? Right. So that depends on the satellite, right? So you've probably learned in aero class from aerodynamics or whatever that the drag force is dynamic pressure times the coefficient of drag. Did I mention that there? Times the area, the area perpendicular to the direction of motion. So exposed area. So this expression for drag is the same actually as the one for airplanes. So specifically, this dynamic pressure, right, is just 1/2 rho v squared, right. And this, of course, we have slightly. This rho depends on time. It depends on on altitude. Now, in this case, right, most cases, well, mostly, drag force has a component only in the tangential direction. So here's our satellite, here's our RTN coordinate system, right? Unless we're dealing with a space plane, and we sometimes do, the drag force just acts perpendicular, just acts in the same direction as the velocity, but in the opposite direction. Well, no, in the same line as a velocity, but in the opposite direction. So here's our satellite. It's moving at velocity here in the tangential direction. Here we sort of assume a circular orbit, so that makes life a little bit easier. And the drag force acts in the opposite way. Now, in theory, right, we could have some lift, which we were not going to account for, right? So space planes, for example, would have some lift, and actually lift could go in this direction, but it could also actually go in the normal direction. So you could actually do a plane change if you had a space airplane or something like that. But typically, we're going to assume that the normal component here is 0. We're going to assume this quasi-circular orbit so that the tangential component is 0. So both of those components we're going to ignore. Okay. So we'll just assume that the velocity is in the tangential direction. We'll also ignore the rotation of the Earth, which, the atmosphere moves along with the Earth, right? We don't have like wind blowing us all off our houses at going at 0.5 kilometers per second. It would be very windy. Although I guess that Aristotle, that was his argument against, rotating Earth models, is that like there'd be a 0.5 kilometer per second wind. So maybe there is, or maybe the Earth's not rotating. Who knows? In any case, so there is actually a wind in space of 0.5 kilometers per second because, remember, everything's in the ECI coordinates. But we're going to ignore it. Right. And so, okay, we got our force here, expression for our force. It's solely in the tangential direction, right? Tangential. We're going to ignore the components in the normal and in the radial direction. Its magnitude is given here, right? We've normalized it by per unit mass. And in here we've replaced, right, this the CDA over m with this ballistic coefficient. So not because we're shooting things, but because basically we're going ballistic at this point. Not out of anger, but because we are just we're ballistic. So this is the expression for ballistic coefficient. So obviously, the larger the ballistic coefficient, the higher the mass to drag ratio, basically. So this is unitized per unit mass. And so now it depends on the ballistic coefficient. So the higher the ballistic coefficient, the less drag affects you. So everything we're going to be talking about will be helped if your spacecraft is more massive. So like the International Space Station is more massive than most sets, like a CubeSat, and so it has so ISS, for example, has a large ballistic coefficient, and a CubeSat has a small ballistic coefficient. Again, Q is dynamic pressure. V is perpendicular to the orbital plane, perpendicular to H. A is the area projected onto the plane. Coefficient of drag. Well, that will depend actually on how aerodynamic your spacecraft is. So, for example, Sputnik or something like that, right, has a low CD, and something like this with say solar panels has a high CD. Now, technically, drag can also get us some lift for like a space plane, but we typically ignore that component. But if you're a space plane, you can actually use drag to make changes in your orbit. So that's fun. All right, so now let's look at the effect of drag on your orbit. So first of all, right, notice the drag by definition, unless you're a space plane, has no normal component to it, right? So it's in the direction of motion, right? It's not going to change your It's not going to change your angular momentum vector. Right? It will change your energy, and it will probably change it to the less. It will decrease your energy, sap your energy, but it will not change your angular momentum vector. At least not the direction of it. The magnitude can change, right? So I guess the normalized version of this actually doesn't change. Actually, so I should write that. Okay. So for now, we've assumed that the eccentricity is 0. We're in a circular orbit. And so really there's no effect on eccentricity. So E dot equals 0. And so we're going to focus on the effect on semi-major axis, because that's the energy of the orbit. That's what's decreasing, basically our radius at this point. So we'll ignore eccentricity. So obviously that goes to 0. This goes to 0. So all that bits goes to 0. And so all we're left with is a cubed over mu, rho over m, and then v squared. So v squared, right, we're doing mu over r, right? In this case, a, I should say. And so we plug all these numbers in. There's mu over a. Let's see. We've substituted in for the ballistic coefficient. Right, and of course, obviously, the change is negative. Right, so we're decreasing our semi-major axis. Our orbit is decaying, and so this all simplifies out very easily. That cancels that to the instantaneous rate of change of our semi-major axis is equal to basically the size of it, and the most important factor are these two things. The density of the atmosphere, which is going to be proportional to how high up we are, and the ballistic coefficient. So if we move A to the other side and we integrate the left and the right-hand side, we can explain, so we move there and we integrate both sides. We can, assuming a constant density, right, assume constant density, right? We can obtain an expression for A. But of course, we can't use a constant expression for omega for density, because we see that the density as we go downhill will be increasing. Right? But it's a very simplistic expression for the semi-major axis as a function of time can be given here, assuming a constant density. Unfortunately, of course, the density is not constant, and we can sort of see that here, right? So what we see here is the altitude plot for the International Space Station as a function of time, right? And so this is a year, right? And we can see that the change in semi-major axis, right, over a year is quite substantial. So this is looks like 15 kilometers. This looks like 30 kilometers. This looks like 5 kilometers. So a delta in that year of 45, 50 kilometers. Right. So the space station is only orbiting around 380 kilometers to begin with. So if you're losing 50 kilometers in a year, right, then you're going to very quickly not have an International Space Station. So obviously you've got to boost your altitude. So there's a delta V budget for that. But things get worse. So things get worse. So look at this year. That was 1999 to through 2000. The very next year, right? Look at this, right? So the very next year, we have a decrease in altitude of 10, 20, 30, 40, almost 50 kilometers. Let's just write 50 kilometers. And not even half a year, right? And so we get, here's another decrease of 20, another decrease of 30, say 35, because there's some like little mini decreases here. And so in this year, actually, the delta A is 50 plus 35, 85, 90 is 110 kilometers, right? So 1 year, the natural decay of the orbit is 50 kilometers, and the next year, the orbital decay is 110 kilometers. And then we can actually go over here, right, into another year. Let's say this year over maybe here or something, right? And we could estimate that the delta A is only 20 kilometers or something like that, right? Maybe 25. Right. So this tells you several things, right? It's not just a function, right? This is also low in the atmosphere. So what this tells you is that A, you need a lot of delta V to keep spacecraft in space, especially at these low altitudes where the space station lies. And then second, it tells you that, right, that number isn't constant, right? They let the space station get really low this year. I don't know if they ran out of fuel or what, but clearly they did not plan properly, and then they had to spend a lot of delta V getting it back up. Whereas over here in a good year, right, you only decay by 25 kilometers. And why the difference? And the answer, of course, is that rho changes with time. The density of the atmosphere, even at a fixed altitude, changes with time year to year, right? It's not day to day, although there's some of that, but it's mostly year to year due to activity of the sun. So, right, the atmosphere, right, is a continuous fuzz, right, that lives around the Earth, right, and it decays as you get farther out, but it varies continuously, and it goes all the way to a density of 10 to the negative 3 at sea level, us, right. And it's very predictable up until the Kármán line. So the Kármán lines, again, where a spacecraft in circular orbit at the Kármán line will not survive a singular orbit. You can make an exception if you're in a highly elliptic orbit. Right. But beyond the Kármán line, things get very dicey. Right, it's very difficult to model the atmosphere beyond the Kármán line, and especially once you get up in the ionosphere. Right. So again, above the Kármán line, we're officially astro people. We don't like those arrow people. And that variation is due to, right, the reason that atmosphere is there to begin with, which is it's trapped in the Earth's electromagnetic field. Right. And the problem, of course, is that Okay, here's the Earth, right? Here's the magnetic field lines. Let's see, actually, that's a bad magnetic field line. Can I just dump that? Right, there's our magnetic field lines. Right, and normally, right, our ionosphere, right? Oops, let me undo that. Make a different color, right? You normally the atmospheric particles are trapped. They oscillate. They're ionized, so they oscillate about magnetic field lines, right? The problem is, of course, then that the sun, right? Am I using? Let's see, green, right? The solar wind, right? Also producing charged particles. Say, well, there's no such thing as a positive electron. So let's say alpha particles, positively charged alpha particles or something like that, right? They, charged particles produce their own magnetic field. And so they interact with our magnetic field lines and push them, right? Push these magnetic field lines. Right? So now our magnetic field lines, right, look more like this. So that some of the charged particles, right? Some of the charged particles are closer to the surface, but some of the charged particles are now farther out because that same field line on the other side is pushed farther away, right? And so it's these particles that are the problem. Because remember, you orbit all parts of the Earth, right? So if you're in an orbit up here, right, it's these particles that you're encountering that are causing the problems, right? So overall, right, the density is not is sort of uniform, but the part that you encounter, it gets worse when there's solar wind. Right, and so the density of the atmosphere up in these higher altitudes varies dramatically with the sun, and so that's what we're seeing here. So at lower altitudes, 300 kilometers, we're getting closer to the Kármán line where the ionosphere isn't as much of a factor. But as we get farther out, right, the variation between an active sun and a quiet sun, right, becomes more substantial. Right, this variation increases as we get farther out because, right, we have fewer particles to begin with, but then when we have an active sun, we're pushing, some of those inner particles out farther. Right, and so these lines will eventually meet up, right, at some point. Right. And so we get very little variation down here at the Kármán line. But then when we get in the ionosphere, and as we get farther up in the ionosphere, in fact, we get more and more variation. But eventually, of course, nature takes its course and the ionosphere quits. But in these intermediate altitudes, 300, 400 kilometers, things, they vary a lot. So let's see the implications of that. All right, so this is delta V budget. Right, this is a plot of delta V. Right, basically the delta V you need meters per second, not kilometers per second, meters per second per year to maintain for orbit, right? Per year, right? So delta V per year you need to not fall out of the atmosphere, to not decay your orbit. So obviously, like down at the Kármán line, everything meets up, and right, nothing matters, and you need a lot of delta V to maintain your orbit. So that's like kilometers per second, obviously. So you can't maintain your orbit at the Kármán line. We already know that. But real orbits, where do real orbits start? Real orbits start around here, right? 300 kilometers. Basically, 300 kilometers is sort of a minimum orbit. And you see these numbers diverging, right, as you get farther out. And that's because of that effect. And then ultimately, they sort of converge back to zero because, right, I mean, there's a logarithm plot, but they converge back to zero because the ionosphere just doesn't go that far. But but in this area, right, there's a lot of variation. And so we see, so what we got here, right, is normalized for ballistic coefficient, first of all. It's in, fortunately, SI units. And so it's actually for a ballistic coefficient of 100. So if you have a ballistic coefficient of, say, 200, you have to multiply this number by 2. So actually, I should put delta V times ballistic coefficient divided by 100, really, is that. Actually, so the actual delta V is this delta V times the ballistic coefficient divided by 100. All right, so anyway, so what we see here is like at 300 kilometers, between 300 and 400 kilometers, right? We look at the difference between an active sun and a quiet sun, right? Right, and a quiet sun, our delta V budget is very small, right? Only 100, say, for example, meters per second per year, right? Relatively small. Versus we have an active sun, right? Oops. We have an active sun, and all of a sudden our delta V budget has to boot up to, say, 800 meters per second per year. So almost a kilometer per second per year at a solar maximum. So you remember that the space station floats around in this range. If you get up to 400, of course, this gets back to 100 meters per second. So obviously, the higher in your orbit you can maintain yourself, the less delta V budget you require. But you can see the problem, right? If you budgeted delta V for a solar minimum, and then you actually launch into a solar maximum, you very quickly run out of propellant, and then come down much earlier than you anticipated. Once you get out here, right, it doesn't matter too much because, right, this is like 9 meters per second per year. So, you know, not a whole lot of, it's called station keeping. So not a lot of delta V is required for station keeping when you get in this 500 to 700 kilometers. But honestly, most near-Earth satellites are in this range. So near-Earth satellites typically don't last that long. I believe, actually, I should look up where the that new Elon Musk's new satellites are launching into. Hopefully, they won't live there forever, or maybe they. I don't know. They seem useful, so maybe I do hope they do. So again, if your ballistic coefficient is actually 10 times lower than the listed value, then you need 10 times the delta V. So these are for relatively heavy spacecraft. So if you have a CubeSat, CubeSats need more delta V. But they typically don't have it. Typically, CubeSats actually don't have any delta V. And so we get to the other curve, which is the lifetime. So if you don't have delta V, so no station keeping. So the definition of lifetime is the time it takes the spacecraft to reach the Kármán line, after which it won't survive a single orbit, which in an orbit is about an hour and a half. So basically, it's dead. Right. These are so we have two units. We got the customary units and the SI units. The ballistic coefficient here in ballistic coefficient actually does depend on which units you're using. Here it's using customary. Okay. So how long will your spacecraft last if you don't do station keeping, basically? And the answer is, of course, not long. Right? So let's take a normal, sort of nominal spacecraft here at a 300 kilometers, let's say, altitude, sort of normal spacecraft altitude. We see that maybe it lasts 110 days. So a normal spacecraft, normal one ballistic coefficient, will last 110 days at a 300 kilometer orbit. So not long. You boost it up to 400 kilometers and you get a lot longer, right? So 400 kilometers here. Regardless of which ballistic coefficient you have, we could sort of extrapolate that out, right? Here, this still 100. So light spacecraft still won't last forever, but 400 kilometers, a reasonably heavy spacecraft, will last 3 years or so. Right. So again, this actually shows the mean. This is for a mean value. Mean value, that is, of density, of solar activity. Right. Sorry, that's nautical miles, right? My bad. So I should redo all of that, right? So 300 kilometers, so I meant 400 nautical miles and 300 nautical miles. At 300 300 kilometers, your spacecraft lifetime is not much. So your spacecraft lifetime is measured in days. So for again a nominal ballistic coefficient of 1, a spacecraft has 2 days, right, of life. Of course, the space station, you saw how quickly it was dropping out of the sky as it approached. It was down to 310 kilometers, and the space station ISS has a relatively large ballistic coefficient, so it's maybe up there. But still, once it gets down to that 300 kilometer altitude, its lifetime is in days, in months, maybe 2 months. And then, of course, what we get here that was actually in a solar maximum, and so actually the number will probably be farther down. Okay. And then, of course, you've got Skylab, right, which didn't have any station keeping. And even though it had a relatively high ballistic coefficient, it had the unfortunate problem of launching into a solar maximum. Into solar max, and it basically had people on it for a very short period of time. I forget exactly how long it lasted, maybe a year, something like that, and then it burned up. So here's how the lifetime varies with, of course, the atmosphere, right? And so we're going to be focusing again on that 350 kilometer range. This is for a nominal ballistic coefficient of 1. Again, this is in customary units. To convert to SI units, we multiply our. So this is we multiply by 0.02. So this is that's in SI units. So we multiply by 0.2, divide by our ballistic coefficient in SI units. And then we take the number we get over here, right? We plug that in. So we get this number multiplied by 0.2 divided by the ballistic coefficient in SI units. So we see various lifetimes here. This is for quiet sun. This is for an active sun. And here, let's focus on the 350 line. We see that in a quiet sun, Normal sort of small-sized satellite, medium-sized satellite will last 10 days, maybe 11 days, 12 days. And that's a good day. That's a good sun, right? And then the same 350 kilometer orbit here lasts 1 to 3 days in a solar max. Right. So same satellite lasts between 3 and 12 days, depending on if you're in a solar min or max. The difference is more substantial out here, maybe 120 days at 450 versus say 12 days at a solar max. Right. So again, to get your actual number, right, you multiply by 0.2, divide by your ballistic coefficient in SI units. This is normalized to 1 in customary units. We can take this plot out further, and then as we get out further beyond 600, now we're estimating our lifetime in years, right? So same conversion rate, right? The predicted times 0.2 divided by ballistic coefficient. We again see this large range, right? From a solar max. So here we have 2 orders of magnitude. Again, as you get farther out, that magnetosphere, the solar wind is, right, that effect is increased, right? There's normally no atmosphere out there, but when there's a big solar wind, right, it's a big solar wind blowing in, right, it pushes those outer field lines up, and so we get these particles, which are normally way down here, way out in the atmosphere. And so we do get some drag, and so then we have these lifetimes even for out to 750 kilometers where you only survive a year. Right? Whereas normally in a solar min you'd survive 60 years. Right? So 2 orders of magnitude almost change in lifetime. 2 orders of magnitude change, almost. And then when you get way out, there's still 2 orders of magnitude change, but doesn't matter. Well, I mean, clearly, right, maybe 12, maybe that's 18 years. But solar maxima don't last 18 years, so at this point it doesn't matter. Let's see. See if we can adjust this. There we go. So okay, I've said that lifetime delta V budget depend on solar maximum. Right. These both depend on solar activity. Right. So how can we predict solar activity? Right. So obviously, solar activity depends on the sun. The sun is a very chaotic beast. Right. It has its own magnetosphere. Which traps out the particles, but it also has solar flares, which escape that, and so basically it's hard to predict. Typically, however, we have cycles. We have this 7-year solar cycle, right? It looks like 7 years. Let's see. So if it was 7 years, it would be 86 to 93, right? So 93. So that's 7 years, right? So the cycle lasts approximately 7 years. It's not rocket science, we don't really understand it. But on average, right, it's the solar cycles rise and fall every 7 years. Some maxima, some cycles increase more than others, but generally this is a good time and this is a bad time. Careful, and then good times. Right. So how do we this? So what am I plotting here? Right. So this is the. So what I'm plotting here is actually, it's how do you measure the solar weather? Right. I mean, so this is a measurement that people take, which is basically the power flux at a particular wavelength. Right. So there's no real metric for how active the sun is. Right. The degree to which it bends the Earth's magnetic field lines. But we find that there's a good correlation between this the power density at F10.7 and sort of the bend in the field lines, right? So this is like something we can use to predict density. So a lot of effort goes into predicting these solar cycles, but it's really hard, right? So, for example, here's we have this. This is the Shatton model of solar activity, Shatton weather model. Basically, you're predicting something like crazy chaotic, which is the sun. And so really, I think these are just curve fits, right? I mean, you could use machine learning and probably come up with something better. But then it's hard to, I mean, it's just not predictable. So you can see here, this was the prediction of the Shatton model. These are the standard deviations. And not only did the magnitude get wrong, right, because we're outside the magnitude, but the timing got wrong, right? So the maximum occurred here as opposed to here, right? So imagining that like you planned on having low delta V down here, and actually, so you didn't budget for the solar maximum, and suddenly, so you launched into here and launched into a solar maximum when you were meant to be planning for a solar minimum. Well, then you get a Skylab type situation where you have a delta V budget shortfall. And then of course you're having concerns that you're going to fall back to Earth like Skylab, and then you're blaming Shatton for coming up with a crappy model. Shatton your pants, perhaps. I shouldn't say that. That's like, yes, I'm recording this, so ignore. Hopefully, no one's listening at this point. Anyway, so what was I doing? Yes. So that's the effect of drag on circular orbits, right? So that was all for circular orbits. Now we consider briefly the effect on eccentric orbits. Unfortunately, we don't have good models for this, right? So we do the best we can. So for example, remember we had that expression for E dot. Right? We had that big complicated expression, but that required a good model for atmosphere. So what we've done is we've taken that expression for E dot, we've plugged in a model for atmosphere here. Right. So we've plugged in a model for atmosphere over a revolution. We've integrated it, and we get the change in eccentricity over a single orbit. So here we go. This is the There's the exponential density model. We integrate that over an orbit to get the net change in eccentricity over that orbit. Of course, it's always decreasing, right? We see that here, is that the eccentricities are decreasing. Why is that? Well, I mean, it's fairly obvious, right? The drag force is all acting at periaps, right? So very little drag force at apoaps. And so, obviously, forces can't change your position. They change your velocity. And so what does a change in velocity at periaps do? Well, it changes your apoaps. It doesn't change, so no delta radius of periaps, but there is a delta radius of apoaps. Obviously, if there's some drag force here, that will change your periaps, but what typically happens is this way, the significantly out, the effect of this force is significantly greater than the effect of that force. And so what it does is it reduces apoaps until it matches basically periaps, and at which point you have a circular orbit. So E dot, right, decreasing. The effect of drag is always to reduce eccentricity. And this just gives an expression for how much it's reduced over a single orbit. Right. So these i's are Bessel functions. You don't have to worry about it. Height, well, it's a fixed height. Anyway, the expression is just to give an idea of what kind of forces we're talking about. We probably won't have to work with that particular equation. So we're almost done here. So this just illustrates that effect, right? That the drag forces are mostly mostly acting here at periaps, and the effect of that drag force at periaps is to lower the radius of apoaps, whereas there's low drag force at apoaps, and so there's no reduction in periaps. So you get this sort of counterintuitive effect where even though all the drag is acting at periaps, all the effect is felt at apoaps. Felt. Right? And so the periaps remains almost constant until you get to like the very last minute, at which point there's some drag here. And so your periaps is decreasing. And so finally you get to a point where the periaps, you get to a circular orbit where the periaps and the apoaps are the same, and then you just drop off the map. Right? So this is, you get to the Kármán line very quickly here. And then you've re-entered. Right? This is pretty much the same, except now it's also plotting the eccentricity of the orbit. So now I do mention, right, in both of these cases, right, the apoaps is not huge. There's still drag happening over here. It's just there's so much more here at the periaps because this is like 200 kilometers. There's so much drag happening at periaps. And here, look, here's their time. 14 days to re-enter. Here's the same thing. Here we get out to 100 days. So the altitude's fairly large. So even though our apoaps is really high altitude, 2,000 kilometers, our periaps is very low, like 200 kilometers. Right. So, excuse me. Bless me. Bless me. Bless me. Sorry. Yes. So I apologize for that, the whole sneezing there. I guess I could turn off the mic for that. In any case, so this lists eccentricity as well as actually this is looks like the parameter here, and altitude. So altitude of apogee, altitude of perigee, and then eccentricity. There is this little line connecting them to. Also, the period is decreasing, so that's period, I guess, period of the orbit. Looks like minutes. Right. So over the lifetime of the satellite, 200 kilometers there's a lot of energy in this orbit, and so does take a while to sap off all that energy. It's all the sapping is doing here, but you see it's steadily decreasing in energy. Oh, sorry, it's this one. Steadily decreasing in orbit. Until you get farther, so there's going to be a delta E at every periapse, and it's going to be more or less the same. And at some point, you get that energy is dropping off quicker and quicker, and why is that? Well, you get it's just because there's not enough energy stored in the orbit to overcome this effect. And then at some point, the drag over here kicks in, and then you get this exponential decrease, and then you have no eccentric E equals 0. You have the apogee and the periapse are the same. You have a circular orbit, and so that which makes everyone nice until you realize that circular orbit means no energy left in the orbit, and so you drop into the Kármán line and you disappear. Took 100 days to do that just because there was so much energy stored in the orbit. Right. Okay. So now we're pretty much done. So we can just play just an illustration of what happens at the last point on that plot. So this is the Japanese spacecraft Hayabusa. Which which is actually visible was visible using a telescope here, and you can see it entering the Kármán line, and there's like tiny little pieces floating, breaking up into larger. So it initially had a very relatively high ballistic coefficient. Now breaking into smaller pieces, much smaller ballistic coefficient. However, there's one piece here that they're still tracking, which still has a relatively high ballistic coefficient because its area has been decreased, but it still has some mass. I don't know what's in that, but something relatively massive. And so that's, my friends, what happens if you don't budget your delta V appropriately. Right, so finally, we've covered the general case, right? What happens to the orbital elements due to changes in due to forces in this satellite normal. Force goes to changes in H and changes in E, which leads to, in the sort of quasi-elliptic steady state approximation, changes in these orbital elements. We covered models of the atmosphere, showed how that led to orbit decays, talked about the effect of that orbit decay on delta V budget and on lifetime. And finally, we talked about the effect on eccentricity and how eccentric orbits have a store of energy which is gradually sapped off until the orbit decays to nothing. In next lecture, we'll talk about the other major orbital perturbation, which is due to the misshapen nature of the Earth, and how that leads to critically inclined orbits frozen orbits. Yeah, sorry. Frozen orbits. Very particular ones which actually have significant usage. And finally, these formulas for taking the effect of these forces, translating them into changes in the orbital elements. All right, thanks for listening. Good luck with the homework when you start doing it, hopefully. And I'll see you during office hours.